Good morning, girls, and welcome to my YouTube channel. I'm sure you've all been following developments over the last couple of days, and if you're looking for answers regarding your exams, unfortunately, I do not have them. I think the only thing we can be certain of is that even if we don't know when your exams are going to be, you are going to do an exam on this at some point. So I think in the meantime, all we can do is just keep going through, try and finish the course virtually via these videos. You can email me or put something on the Google Classroom if you've got any questions, and we'll just try our best because we know that eventually we are going to have to do an exam, whether that's September, the end of next year, who knows. But we'll keep trying to learn chemistry in the meantime. So what we're going to try and do is finish off the topic we're on, which is quantitative chemistry. Now I know we're quite close to the end within class, so I need to go back over a wee bit. But we're going to start on this page, which is page 14. That's just out of your notes, which is about calculation of formula compounds, basically the work we did on empirical formulas. Okay, so I'm just going to go through notes. I'll get you maybe to pause the video at various points to have a go at the calculations first, but then I'll work through them. So it'll help if you have these out in front of you as you look at this video. What I might also get you to do, if I have time at this video at the end, these are some questions from your Bible, your question book that you have for each topic. This is from the quantitative chemistry section. I might do this as a separate video, but we'll see how much time we have. So without further ado, just a quick recap then. So we were looking at the idea of empirical formulas. So we got this idea in chemistry of different types of formula, and if you remember, the majority of the formulas you look at in chemistry are actually molecular formulas, because that's your accurate ones. They're the ones that show the actual number of atoms of each element present in a compound. So for example, in this molecular formula here, we know that this compound has got 6 carbons and 12 hydrogens, and that's what it's got. The empirical formula, which seems a wee bit silly in a way, is basically the simplest whole number ratio of that molecular formula. So in other words, if you cancel it down to the simplest whole number form, that would give you the empirical formula. So as you've got in your notes already, C6H12, that's a 1:2 ratio. So the empirical formula would be CH2. C6H6 is a 1:1 ratio. Empirical formula would be CH. CH4, now you can't actually cancel it down, so the empirical formula remains the same as the molecular formula. So it is still CH4. So that seems very simple. One little calculation you can do between your empirical formula and molecular formula, if they give you the empirical formula of a compound and tell you how much the whole molecule weighs, there is a way you can work out the molecular formula we looked at in class. So just going over that example again. In this question here, a compound has a relative formula mass of 28, so that's the mass of that whole compound. However, its empirical formula is CH2, and I want you to work out the full molecular formula. The simplest way to look at that is actually to analyse your empirical formula, because that's the only formula you've got to go off at the minute. So it is CH2. The RFM of CH2 is a carbon plus 2 hydrogens. Carbon is 12, hydrogens are 2, well, 1 each. So 12 plus 2 is 14. The RFM of the molecule itself, tells us in the question, is 28. And a wee bit of pattern spotting here, you notice that is twice the mass of the empirical formula. So in other words, if we double 14, we'll get 28. That tells us we have to double the empirical formula to get the correct number of atoms for the molecular formula. So therefore, the molecular formula equals, well, basically CH2 twice, which is C2H4. So in the actual compound, which is mass 28, it's got 2 carbon atoms and 4 hydrogen atoms. Okay. Down below there, you've got some test shaft questions. I think we did actually do them all in class. I'm still not going to go through them now, but if any problems with that, let me know. If we go on to the next page here then, this is maybe more of a problem-based question you might get in an exam. I'll go through it quickly again, though I know we did do this in class. So it might give you information in slightly more kind of experimental terms. So 1 to 8 grams of copper combines with oxygen, 160 grams of copper oxide is formed. So this is when we actually happen to work out the empirical formula from data. So it's a very kind of simple kind of method for that. How I generally lay it out is I give a ratio. So between copper and oxygen, we want to work out the formula, empirical formula of copper oxide. So Cu is in a ratio to O. We're trying to find that ratio. What we got from the question is the masses, so we start there. The mass of copper in the question is 128. The mass of oxygen doesn't tell us directly. It tells us the total compound's 160 and copper is 128. 160 minus 128, the only other element there is oxygen, so that must be the leftover mass. That will give us a mass of 32 grams. Now, golden rule is the ratio for empirical formulas does not work if you've got masses. You have to convert into moles first. So do our familiar transformation, divide by the RFM, or the relative atomic mass of the element. 128, periodic table, copper 64. Typing your calculator comes out 2. Oxygen, be careful here, it's not O2, it is just oxygen. So 32 over the mass in the periodic table, which is 16, gives us 2 again. The ratio is 2 to 2. Remember, empirical form has to be the simplest whole number ratio. That makes it 1 to 1. Therefore, the formula of copper oxide is 1 copper, 1 oxygen, CuO. So I think where we moved on from that in class, I'll come back to this in a second, is we looked at some of these questions down here, and I think that's actually where we left off before we school got cancelled. What I'll do is I'll get you to maybe have a go. So maybe pause the video now, have a go at these questions, and I'll just go through the answers very quickly. I'll not do your work now, just give you kind of the correct answers at the end. Anything you need more clarification of, obviously I can give you that as well. So pause now, have a go at those questions there, and then I will work through, or give you the answers to them all just now. So question 46 comes out being MgCl2. 47 comes out being Na2O. 48 comes out being Mg3N2. This one, 49, lead oxide, becomes PbO2. 50 is CH3. And this one, 51, is FeCl3. Now, I'm actually going to look at these two just in a little bit of depth because they're a little bit different. Now, you might have noticed about these ones, 52, 53, is that they're in percentages and not masses, which maybe puts you off a wee bit. The one thing about empirical formula calculations is you actually can treat percentages the same thing as masses, because if we look at this one here, compound contains this percent of silicon and this percent of hydrogen, and calculate empirical formula. So again, it's a ratio between silicon and hydrogen. In our normal method, we will look at the masses of these elements and work out the moles, but we've got percentages. However, if you think, if I had 100 grams of this compound, so 100 grams of the whole compound, and 87.5% of that 100 grams is silicon, 87.5% of 100 grams is 87.5 grams. Essentially what I'm getting at is, if you imagine you've got 100 grams of the compound, you can just treat percentages as masses in grams, because a percentage of 100 grams is just a certain number of grams. So for this, all I can do is work out 87.5 grams, because we're imagining it's 100 grams. Hydrogen is 12.5 grams. So I do a very quick calculation here. The mass of silicon is 28. So 87.5 divided by 28 gives me 3.125. Hydrogen is just 1, so 12.5 over 1 is 12.5. Now that's not the easiest ratio to see. So if I take 12.5 and divide by the smaller one, which is 3.125, that'll get me 4. So it's clearly just a 1 to 4 ratio. So the empirical formula must be SiH4. Okay, similar idea with this one here. Now this one's a little bit more tricky because you've got a missing element. It's between carbon, fluorine and chlorine. So C, F and Cl. Don't think we've seen one with 3, but use treat it the same. Again, it is just percentages, so just treat it like masses. 14 grams of carbon, 44.4 grams of fluorine. The remainder is chlorine, therefore I have to take these percentages away from 100 because percentages are out of 100. So 100 minus 14 minus 44.4 gets me 41.6. So that's the masses. The moles next, so 14 divided by 12 is 1.17. Let's go 2 decimal places. 44 divided by 19 for the fluorine is 2.33, or 2.34, sorry. 41.6 divided by 35.5 for the chlorine gets me 1.17. So again, these are kind of unusual looking decimals, so I can just divide by the smallest one. That gives me 1 to 1, 2.34 divided by 1.17 is pretty much exactly 2. Therefore the empirical formula becomes CF2Cl. So that's a very standard calculation, giving you some data on the masses of elements in the compound. Remember, masses first, then moles, then simplest whole number ratio. That gives you your empirical formula. So we're almost there with the empirical formula. There is just one final thing that can come up in the exam, and it's a slightly more experimental version of that. They could ask you, how would you work out the empirical formula of a compound? Now, it's not going to be a very complicated one. Generally, it'll involve a metal reacting with oxygen. So if I kind of run through the concept of that, if you had a certain mass of a metal, for example, magnesium, if you wanted to work out the formula of magnesium oxide, you would burn this because it would react with oxygen. So you'd stick in the crucible, you would stick on top of a tripod with the gauze, etc., and you'd heat it for ages. What you'll notice then is once you've heated it, it will get heavier. And you're thinking, well, will it get heavier? It's getting heavier because it's now the oxide. So it's not magnesium by itself, it's magnesium oxide. Now, no instinctively you probably think, oh, I would just do a swap and drop. That would work out the formula of magnesium oxide. But in this type of question, you're not allowed to do that. You have to do an empirical formula calculation. So I know it's got heavier because oxygen is now joined to this oxygen, or to the magnesium, sorry. If I work out how much magnesium I had at the start and how much oxygen I had at the end, then I can do my normal calculation, like I've got kind of up above where you got two masses working into moles. They could ask you a wee question for the steps of how you do that, so just run through them quickly here. Obviously, you have to be a wee bit careful with your masses you're using here, because I need to, the way the crucible I'm doing this experiment in first to take it away at the end. So for step one, weigh your crucible in the lid. Now, you will actually need a lid in this experiment. Just if you imagine a saucepan at home, a lid allows heat to get built up to get hot enough to react. However, in step 3, it says heat it. It says use tongs to raise the lid occasionally to allow air into the solid. Obviously, if this magnesium is reacting with oxygen and it's trapped by a lid, the oxygen is going to run out. So I'm going to have to lift it up occasionally, just let a wee bit of air in, or oxygen in, sorry, to go along with the heat I've built up with the lid. Gone through it a few times, but essentially I know how much to do, because if I stop after a wee while, let it cool down and weigh it, I'll get a mass. Then I might heat it again, just in case it didn't heat it enough. The way I know that I've heated enough is if the mass remains constant. So if the mass increases by 2 grams the first time, then after another heating it increases by another 0.1 gram. And then at the third heating, it stayed the same, so it's only gone up by 2.1 grams. I would know at that point I've added all the oxygen I can. It can't get any heavier. So beyond that, that's just the method you have to go for. So that could be like a theory question in itself. The next thing is just look quickly at how that comes up as a calculation. So there's one example on the next page of your notes. Feel free to have a go at the first if you think you can work it out, but I will just go through it now. So thing to get in your head is this is not different calculation-wise to the ones we've done down here in terms of working out masses, moles and ratio. It's finding the masses a wee bit more tricky here. So here's the general method. It's going to guide you through in steps, but I'm just going to plonk to the right hand side here, our normal kind of working out. This is for magnesium oxide. So I'm trying to get the empirical formula, the simplest whole number ratio for magnesium going along with oxygen. My first step in my normal method is to work out the masses. I need to find the masses, and if you notice here in the method, that's the first kind of, well, step 1 and step 2 and 3 going together. Step 1. Calculate the mass of magnesium used. So I'm going to need that for this bit of my working out here. If I look at the data I've got the mass of the empty crucible and its lid, the mass of that crucible plus plus magnesium, and then mass after it's heated with the crucible lid as well. The mass of the magnesium by itself will just be the 41.12, these three things, minus the 35.60, because if I take away the mass of the crucible and lid, away from the mass of crucible, lid, magnesium, I'll just have the mass of the magnesium left over. So if I do 41.12 minus 35.60, I end up with 5.52 grams. So I'll put it there beside it working out, also in my working out over here. I need to work with the mass of oxygen, but it's required to do that just in one step. If I look at it here, the mass of magnesium oxide formed, that would be the mass of the final one, 44.82, minus the mass of the crucible and lid, because again, if I take away crucible and lid from this final one, I'll just have the mass of the contents after heating, which is just magnesium oxide. So 44.82 minus 35.60 gives me 9.22. Mass of oxygen gained, so that's the mass gained of going from magnesium to magnesium oxide. And that's just 9.22 take away 5.52, because that's only got heavier because you've added oxygen to it. So that gets me 3.7 grams. At that point, that's what I need for the mass of oxygen in my normal working out. So I hope you see that after all this kind of interpreting this question, I have just got a bit of working out, which looks pretty much identical to what I normally do. Mass of this, next step is moles. Divide by the MR, so 5.52 divided by 24 for the magnesium gets me 0.23. Mass of oxygen, 3.7 divided by 16 gets me 0.23. Surprise, surprise, it's a 1-to-1 ratio. Therefore, the empirical formula of magnesium oxide must be MgO. Okay, so very quickly, I think I've got a wee bit of time, so before my camera dies, what I'm going to do is look at the questions from your Bible. So 2 relevant questions are these ones here. So this within the quantitative chemistry section 1.7 of your questions in your Bible. Going to look at question 9 and 11. I'm going to start with 11 and work back to 9. What I suggest, just going to get the most out of this, is if you actually have a go at this first, check you understand it. So have a look at question 11. Have a look at question 9, pause this video, come back to it, then I'll go through the answers very quickly with you here. Okay, so have a quick pause and then have a go at that. And now that you're back with us, hopefully, just going to get my mark scheme out. So this first one, question 11, it's a little bit simpler. It's a 5-mark question though, so they do give you quite a lot of credit for this. Gives you information about a tooth whitening thing called urea, blah blah blah. 20% carbon, 6.6% hydrogen, 46.67% nitrogen, and 26.67% oxygen. Determine the empirical formula. So again, it's a percentage one, but we just treat that like grams. The only thing that's a bit tricky is the fact that we've got 4 of them, but that doesn't change how we approach it. So we've got carbon, hydrogen, nitrogen, and oxygen. Masses are 20, 6.66, 46.67, and 26.67. Moles is basically the mass over the atomic masses, so 20 over 12, 6.66 for hydrogen over 1, 46.67 over 14, and oxygen is 26.67 over 16. Calculated, that will come out as carbon is 1.66, hydrogen is 6.66, nitrogen 3.33, oxygen 1.66. You may well be able to spot the ratio here very simply, but we can divide by the smallest number, which is 1.66, gives me a 1 to 4 to 2 to 1 ratio. Therefore, the empirical formula becomes CH4N2O. Moving quickly on to this one. This looks similar to the one we got in our notes, so it's giving you a metal titanium to form titanium oxide. You want to determine the formula of that oxide. So you're in the standard method, put it in the crucible, heat it up, lid on top, lift the lid from time to time. Gives you some experimental data similar to what you've got in your booklet there. Part 1 suggests why it's necessary to lift the crucible lid during heating. Again, we talked about that a second ago. It's to allow air to enter the crucible to do the reaction, because it's going to get used up if we don't let a bit more air in throughout the experiment. So, just gives you a big blank page, 6 marks, to work out the empirical formula. So we've got 3 masses here. I need the masses of my titanium and oxygen. It's going to lay it out like this, like we do normally. Mass of titanium, need to do a recalculation for it. So the mass of the crucible is this. If I add titanium, it goes up to this. So if I take 18.34 minus 18.34 take away from 19.36, that will give me my mass of titanium. That is 1.02 grams. Mass of the oxygen, now I can do it a couple of ways. I can do it a wee bit quicker than I did before. The only reason this titanium has got heavier is by adding oxygen to it. So that's the only difference. The crucible is still the same, titanium is still the same. There's now just titanium oxide in here. If I take 19.36 from 20.04, that will give me the mass of oxygen that I added, and that is just 0.680 grams. Normal method, calculate moles of those both. So 1.02, use the mass here, 48, and 0.680 divided by 16. My moles become 0.02125, and oxygen 0.0425 here. Ratio, you might see that, but that is just, I can divide both by the smaller one, again if I'm not sure, but that is just a 1:2 ratio. Therefore the empirical formula is titanium oxide TiO2, all for 6 marks there. Okay, so hopefully you followed along there. I'm going to do another wee video for the last bit of the book, which is War of Crystallization, and I'll probably set you a few wee questions just to have a go at yourself and to marking and get back to me. Okay, thank you guys.